Hello folks, this is Tom from anti-proton.com, and it's been a long time that you've known me, and I think we've gotten to the point now where I can say this for sure. I wanted to propose to you. See? No, I'm just kidding. These are uranium gems. See, you thought I was serious for a minute. These are uranium gems. Now, when I say uranium gems, they're actually uranium glass, like depression glass. So, hold on. Alright, so there it is up close to the camera, and as you can see it looks just like uranium glass, like you'd find in depression glass at like a junk shop or something like that. And that's precisely what it is. It's made by people. This is not the natural form of uranium. This is the natural form of uranium. So we're getting 32 counts per minute on a Geiger counter. Let's see what happens with the uranium. So let's get that uranium in focus and see what we get. Looks like about the mid 400 counts per minute range, and since we had 38 counts to start with, more or less, so we can say a little over 400 counts per minute is what we're getting off of this. So if you put this on your arm, you put this like you made a ring out of it or something, put it on your hand, it's not going to make your finger melt off or anything like that, and your actual cancer risk isn't really going to go up that much from being anywhere near this. This is negligible radiation, to say the least. And before all of you go running out there screaming that that can't be true, take a Geiger counter, put it up against a container of light salt or something like that, and see the massive difference that makes. Should get over 500. Let's see. The Geiger counter is fun, but this RAP-47 thin crystal cesium iodide thallium doped probe will do a much better job. It has a 1 millimeter thickness and about a 25 millimeter width. So this guy right here is meant for detecting X-rays. That's pretty much what it does. So we're going to take it down here and point it at the crystals. And just to remind you, on the face of this guy right here, you may or may not be able to see the dial, but 0, 100, 200, 300 counts per minute is what it's currently set to. And I'm going to change this to the times 10 mode, this 1960s era Geiger counter. And now that it's on times 10, this is 0, 1,000, 2,000, 3,000 counts per minute. We were getting about 150 counts per minute more or less a second ago. So let's get this guy in good focus and put this over top of the gems here and see what we get from the gems. 500 counts per minute. Anything more? And you notice the scintillator has an extremely quick response, especially this one. About 500 counts per minute. Not bad. So we're getting X-rays off of this. So if you wore this as jewelry, you'd also be getting X-rays. Wouldn't that be cool? Weirdly enough, it really doesn't show up very much on the, let me move this over here, on the Ludlum. Alright, now this right here is a Ludlum Model 12. It's a modern day rate meter. It's kind of like the CDV 700 you saw a minute ago, except this is a much more modern version of it. And I have a 1-inch sodium iodide detector. It's much more sensitive to higher energies than what you saw a minute ago, and I don't think it's going to do a very good job. It's on a times 10 scale, so you're looking at about 1,000 counts per minute. And we put this right on top of those crystals, mash it on down there, you barely get anything. There's no real change that you can see with the naked eye. So let's cut the sound off. We can take this now and put it under a black light and take a look and see what it looks like, and then we're going to toss it on the gamma spectrometer and see whether or not we can determine why it's radioactive. And I'm just going to tell you right off the bat, it's definitely uranium. But is it natural uranium that's been refined chemically, or is it depleted uranium? It could be depleted uranium. It's probably natural. We'll find out. Alright. Yep, they definitely register in the black light. As you can see, the black light indicates for sure these are definitely uranium glassware pieces. The ultraviolet here, the ultraviolet light is fluorescing in the uranium itself, and this has had nothing to do with it being radioactive, by the way. That's a common misconception. It has to do with the chemical nature of uranium that it fluoresces. Well, this particular state of uranium, not all states of uranium fluoresce. For that matter, Your shoes are probably fluorescent, as are probably 100 other objects sitting around your house, and they're not radioactive. So now let's put this in the spectrometer and see what we get. Isn't that cool? So as you can see, here are the gems, and here is the 2-hour spectrum that we took. We have 1,024 channels across the bottom. Each channel collects any gamma ray that was detected at a particular energy. So on the right we have high energy gamma rays, and on the left we have lower energy gamma rays, and they filter into these little channels, these little buckets, these little bins if you like, as the energy goes up. And as you can see in the y-axis here, we have the counts of how many were found. So as you can see, for example, right here at 518 kilo electron volts, that's right around 511 channels in. We probably got something like 20 maybe counts total, whereas over here this is probably somewhere around channel maybe like 100, 150, and the energy of about 60 to 70 kilo electron volts, we were close to 400 counts. So anyway, as you can see right here, we have the spectrum. This is the gamma energies that were detected. Now if you look carefully, the yellow is the background spectrum. This is without the gems added, whereas the blue here is the foreground spectrum. As you can see, there you go, that goes right across, and you can see there's a difference between them. This is obviously radioactive, and right off the bat you see these two guys right here, uranium-235 and uranium-235. This is 253, I'll need to change that. But anyway, there's probably a little bit of radium-226 building up in there too, but not by much. This gives this away as being natural uranium that's been refined chemically. Depleted uranium doesn't usually have much of this uranium-235 peak. It's there, but not as pronounced. There's a little thorium-234, thorium-234. There should be some other stuff like protactinium over here, because this is 1100 keV, so you should see it. You don't, and then maybe because the spectrum might be drifting off a little bit over here, it may have been just a bit further to the right, well, farther to the right. So this is definitely natural uranium. That's the dead giveaway right there. This nice pronounced peak at uranium-235. We could quantitatively actually measure these and the efficiencies and calculate that exactly, but I can eyeball it and easily see that it's dead on for what I wanted. So anyway, if you recall, not that long ago, I measured this cat, this uranium glass cat. It had exactly the same material in it, and if you don't believe me, here's the spectrum. Look at the spectrum. See? The same exact bumps. We're looking more like at this area, right? Well, probably more like to about here. That's what we were looking at in the spectrum a minute ago. This one was done a little bit wider, and you picked up the potassium 40 peak and the Pa 234M over here. But that was a uranium glass cat. So your question now becomes, which is better, the uranium glass cat or the gems? I'll take the cat any day. But anyhow, this is Tom from anti-proton.com, and thank you for watching this, and hopefully I'll be putting out a new video pretty soon, which involves Brazil nuts as soon as they arrive in the mail. So, bye-bye.